So thank you guys, and thank all the participants who have joined at different time zones to listen to the talk today. Thank you guys. So the title of my presentation is Model-Based Process Control in API Manufacturing, a QbD-Vantage. Now this was a case study I did a couple of years back, which wasn't part of a main project work. It was literally a case study, and I collaborated with my colleague Mark Greenfield from operations to discuss certain aspects in terms of impact of control strategies that would be on the quality when we transfer it to a manufacturing plant and so forth. So it was a good collaboration working with Mark. I will talk a little bit more about the motivation of the work and give you an introduction as well. Here's the outline for the talk today. After I speak about the motivation for this work, I'll give an introduction to the case study itself, and then go with the control strategy which would apply in a conventional sense in the absence of a model for the process. Then I'll talk about the model development with Dynochem and a few model-based control strategy options that we came up with. And finally, I'll talk about handling excursions that might happen in manufacturing setting and how we would go about managing those. So if I just take the Dynochem model, I can simulate a reaction profile for a given set of input conditions. Now what you see on the screen is a simulation of a reaction profile where the BOK API was about 10% to start with, and as you would expect over time, the product level keeps going up and sort of maximizes before it starts coming down as more of the API byproduct is formed, and the red trace for the API keeps building up. So this optimum reaction endpoint is what we would really like to achieve. It does two things. One, ensures that the starting material is consumed below 1%. That's the must for the process, and also it ensures that we don't lose to the byproduct formation. So at this point, we have seen what the reaction is, what the model was, what the assumptions are, and we looked at the data and all of it. At this point, we have what we can say is a design space represented by the optimum reaction time, and that space is this particular surface or the plane that you can see. So from this point onwards, we are going to focus on this nice colorful plane that you see on the screen. What we wanted to do was to see if we can represent this surface with a mathematical expression so that we can use it for our control strategy. And finally, all of these things have to be implemented with the regulatory strategy in mind in terms of what is a critical parameter, and if certain thing is a regular testing like an in-process monitoring that's done in the plant that can be maybe more easily eliminated based on the model-based strategy than a critical process parameter. And if it is a critical process parameter, then the level of scrutiny on the model and the maintenance of the model may be higher. So those are again aspects one needs to consider, and especially if we are talking about removing an in-process control, then one needs to have a very good story to show that these models are indeed providing the level of control that the process needs.